So I'm going to solve some model problem, something related to microbial kinetics. In particular, we are going to calculate generation time, or if you want to be specific, we are going to see something related to cell doubling time or cell tripling time, or even if you want to calculate like say for example at each cell division one cell multiplies into or produce 5 daughter cells or 6 daughter cells, then what will be my cell generation time. So if you want to answer that type of question, so this is going to be the model problem. So I'm going to read the problem. So let's say we perform some microbial reaction, say at perfect growth conditions. So try to follow my pen wherever I am drawing at the moment. I'm using a red ink. And what I gave, so here is if the substrate concentration is 10 grams per liter, so you already know what's your substrate concentration. And the monod constants, mu max, which is your maximum specific growth rate, and Ks values are 0.5 R's inverse, and then or 0.51 by R, and then 0.1 grams per liter. So these two are your monod constants. And what I ask you to find is you need to find the time required to triple the biomass concentration with respect to with respect to biomass concentration at any instant of time. So what do I mean by that? Say like if you have a graph like time, say expressed in minutes, and you say x grams per liter, and say if you plot here something around on this line, so from here to here, say like say if you have one cell here and then somewhere around here you have 3 cells, so what's the time in between? So that's something we are going to calculate. And how to calculate, that's what you are going to learn through this exercise. And we are also going to calculate the time required to double the biomass concentration. So what do I mean by this? So in this case, what I've asked is like at each cell division, if you start with 1 say x is equal to 1, after one cell division x will be equal to 2. So for this problem A, if you start with one cell, and after each cell division, so after one cell division, your microbial concentration will be equal to 3, and we need to calculate the time required to for each time how do you say, so for each the cell generation time between each cell division, yeah. So say when time t equal to 0 you have one cell, and say when time t equal to t your x is equal to 3, or time t equal to say tg, we can call tg as a generation time. So what will be the, so we need to calculate this value generation time. Okay, and all we have is time versus microbial concentration. So we have something time versus x. In fact, we don't have this value, but we have monod kinetic constant that allows you to calculate something that you need for this type of problem. Yeah. So let's solve this problem. It's very easy. So you have your monod kinetic constants, say mu max, which is equal to 0.5 R's. So we will solve few problems on this line. And then you have Ks value. Ks value is nothing but the substrate concentration when your maximum, not maximum, when your specific growth rate will be equal to half of the maximum specific growth rate. Yeah. So Ks will be equal to your substrate concentration when mu will be equal to mu max by 2. So how to solve this problem? So if we have mu max, if we have Ks, then obviously we can calculate the maximum specific growth rate using the monod expression, Ks plus S. So let's calculate this value. Mu is equal to, so 0.5 multiplied by And we also have your initial concentration, which is here in the problem. S is equal to 10 grams per liter. So 0 0.5 multiplied by 10 divided by Ks value is 0.1 plus S again 10. So this will be 5 divided by 10.1. So that will be equal to 0.5. Yeah. 0.5, and you should pay attention to the units. Here your mu max is expressed in 1 by r, so mu will be equal to 1 by r. So your specific growth rate will be equal to 0.5 1 by r. And what you need to do now, we need to calculate the time required to triple the biomass concentration with respect to biomass concentration at any instant of time. Okay. Let's continue with this problem. So we have our specific growth rate, which we calculated at now using Monod kinetic constant 0.51 r, and let's assume the growth of microorganisms follow the first order rate law or first order kinetic expression, so which is given by ln of x by x0. So x is your microbial concentration at time t equal to t, and x0 is microbial concentration when time t equal to 0. So when you started your experiment, so you have a fermenter, you add some seed or inoculum, so that concentration will be equal to some number grams per liter. So that's your x0 value, that's your initial concentration, and this is going to replicate or triplicate, so depending on what happened after each cell division. So for part A, what we assume is after each cell division, so one cell goes into 3 cells and 3 goes into maybe, so 3 plus 3 plus 3, so that's 9 and so on. Yeah. So we need to calculate the cell generation time. So what's the time that we need for this process to happen? Yeah. So how to do that? So we know that ln of x by x0 equal to mu multiplied by t. So this is the law that we need for this problem. Just follow the pen. And for this condition, say if you started your experiment when time t is equal to 0, let's say our microbial concentration was equal to x0, which is your initial concentration. So let's say when the time reached the generation time, when the time reached the cell generation time, or let's say after the first cell division, your microbial concentration will be equal to 3 times multiplied by your initial concentration. So all we have x is equal to 3x0. So substitute this value in this expression. So ln of x by x0, that will be equal to ln of 3x0 by x0, that will be equal to your specific growth rate, which is here. Yeah. So mu we calculated just now, 0.5 multiplied by t is nothing but your cell generation time. Yeah. So x0 get cancelled, so tg will be equal to ln of 3 divided by 0.5, so that will be equal to ln of 3 natural log of 3 by 5. So that will be equal to 0.22 hours. So pay attention to the units. Yeah. So if your mu value is 1 by hours, your t will be expressed in hours. Okay. So that's how you calculate the cell tripling time. Hope you are following until this point. So let me give the page number. So this is your page number 1. check page number 2. So, and then we have to still answer part B, which is find the time required to double the biomass concentration with respect to your microbial concentration at any instant of time. What do I mean by that? So let's put page number 3. So what's the time required to double the biomass concentration? So what we are looking at now is, so let's assume the specific growth rate for the problem is same 0.5 hours. This is something we calculated using the monod kinetic constants, or you can just call we calculated using the monod expression. Yeah? So we have 0.5 hours, 1 by r, sorry. And now the condition is after each cell division your one cell split into 2. Yeah, so this is your parent cell, say x is equal to 1 when time t equal to 0. After the first cell division x will be equal to 2. So this is tg in this case after the first cell division. Okay, so we need to calculate the time required. So not time required, the time scale involved from between each cell division. For this condition, say after each cell division each cell split into two daughter cells. So again the same rule, just assume the microbial growth follows the first order expression. So in this case, let's say when time t equal to 0, if your microbial concentration is equal to x0, so in this expression x0 is always your initial microbial concentration or density expressed in grams per liter, for example. So if time t equal to 0, that's my microbial concentration, x is equal to x0. So after the first cell division or when time t reaches the cell generation time. So cell generation time is the time required for the cell division to happen. So that's the meaning out of that. That's the meaning of that. So cell generation time, let's use some notation like always Tg. So when T is equal to Tg, x is equal to 2 times our x0. Okay. So just we know x is equal to twice the x initial microbial concentration. Substitute in this expression. So ln of 2x0 by x0, that will be equal to mu multiplied by t. x0 get cancelled and t will be equal to tg in this case, which is nothing but your cell generation time. That's the parameter that we are trying to calculate now. So tg will be equal to ln of 2 divided by mu. So that will be equal to 0.693 divided by 0.5. So what's that value? It's around 1.4 hours. So pay attention to the units. So if you in the exam you must write the units, if not you will not get the marks. So this is some general problem. So just we are exploiting the value mu. If you know the specific growth rate, then if you know that what happens after each cell division, say after each cell division one cell split into 3 daughter cells or 4 daughter cells, then it allows you to calculate the cell generation time. Yeah. So for example, if just assume after each cell division, then your one cell split into 4 daughter cells or 5 daughter cells, for example, then the rule up the then you can calculate the cell generation time. So if after each cell division, say one cell split into 5 cells, so if your initial concentration is x0, after each cell division your microbial concentration will be 5 times multiplied by x0. Then how to calculate the tg value? So ln of 5x0 by x0, that will be equal to specific growth rate multiplied by tg. If we know the specific growth rate, x0 get cancelled, then Tg will be equal to ln of 5 divided by specific growth rate. So that's all. It's very simple, but you should know how to solve this type problem, and also pay attention to the units. So Tg, and what's the units? If your mu is expressed in 1 by seconds, your t will be in seconds. If your mu is expressed in 1 by hours, your t will be in hours. If your mu is expressed in 1 by minute, then your tg or t will be equal to minutes, expressed in minutes. So pay attention to the units. So that's all for now. I think we can solve the next problem. So this is page number 3. Okay.